You tap a piece of smooth glass in your pocket, right? And maybe 10 minutes later, a total stranger in a car shows up at your exact physical location to give you a ride.
Right, which is just wild when you really think about it.
It is. We're so used to it that we just call it, ordering a car. But if you pause for literally 1 second, it feels like actual magic.
Oh, absolutely. But, I mean, we all know it's not magic. It's this incredibly dense, flawlessly executed set of instructions.
Yeah, an invisible architecture of logic.
Yeah.
And most of us, we interact with it every single day without ever seeing the blueprints.
Exactly. Or, even understanding how a physical piece of hardware, which is, let's be honest, basically just a rock that we tricked into thinking by shooting electricity into it.
A rock with lightning in it. I love that.
Right. Like, how does that rock actually understand human intent?
Well, for anyone who has ever wondered what actually happens under the hood of the software we rely on, this deep dive is, it's your ultimate shortcut.
Yeah, we aren't just doing some basic coding tutorial today.
No, definitely not. We are looking at a really fascinating, comprehensive set of university lecture notes, specifically for CMS705, which is programming languages, taught by Dr. H. Okwu at Rivers State University.
It's a great source. Really lays out the foundation.
It really does. So our mission today is to explore the fundamental DNA of how computers understand us. So, okay, let's unpack this.
Let's do it.
Because setting the stage here requires kind of a complete shift in perspective. When you tell someone, hey, I'm learning to code, they immediately assume you're doing intense math.
Oh, yeah, like you're sitting there doing calculus all day.
Right. But looking at this material from Dr. Okwu, computer code isn't just math. Mechanics-wise, structurally, it is quite literally a language.
And that shift in perspective is mandatory if you actually want to understand how software runs. You really have to look at programming through the lens of human linguistics.
Okay, so how does the course break that down?
Well, the foundation here describes language structure as a system of systems. So, you aren't just typing commands into a void, you are building meaning from tiny individual blocks according to these fiercely strict rules.
Which mirrors a college linguistics class perfectly. I mean, it starts with phonology, right?
Exactly.
In spoken language, a phone is the smallest unit of sound, like the cheesh sound. In programming, you're dealing with the smallest possible tokens.
Right. So we're talking about like a semicolon, a plus sign, or even a keyword like int for integer.
But a single semicolon doesn't achieve anything on its own. Just like a random sound in English doesn't mean anything until you attach it to something else.
Right, which takes us up a level to morphology.
Yeah.
This is where you build those little tokens into actual meaningful units.
So like combining letters to create a word.
Exactly. You combine characters to create identifiers. So naming a variable something like userage or payment status.
Okay, I have my words, but then I have to arrange them. And that brings us to syntax, the grammar.
Yep, the strict rules of order. Subject, verb, object.
So in code, this dictates where the parentheses open and close, or whether a specific math operator is in a legal position.
Right, but here's the catch. Just mashing valid words together into a syntactically correct sentence doesn't mean the machine will actually listen to you.
Right, because if the logic is flawed, the machine just hits a brick wall.
And that is the threshold of semantics. Syntax is just the structural arrangement, right? Semantics is the actual intended meaning of the code.
And this is where I assume the entire process of writing software usually breaks down for people.
Oh, constantly. It's the biggest hurdle.
So I found this analogy in the source material that I really want to test on you.
Okay, let's hear it.
There's this sentence in the notes. So it says, your music is under a book.
Okay.
Now, grammatically, that is a flawless sentence. Noun, verb, prepositional phrase, totally valid syntax.
Sure.
But logically, semantically, it makes zero sense. I mean, you can't physically put abstract music under a physical book.
Right, it's conceptually impossible.
So if I'm understanding this right, if I try to run that exact logical structure through a computer, the compiler catches the semantic error and stops me before the program even runs, right?
Actually, no.
Wait, really?
Yeah, that is a super common misconception. And honestly, it's exactly why compilers can be incredibly dangerous if you don't know what you're doing.
Okay, you're going to have to explain that. Why wouldn't it catch the music under a book thing?
Because what you're describing highlights the critical divide between static semantics and dynamic semantics.
Okay, so the compiler only handles one of those.
Exactly. The compiler is only responsible for static semantics. It checks the grammar and the basic type logic before the program runs.
Oh, I see.
So it looks at music and says, okay, yep, that's a valid noun. It looks at book and says, valid noun. The static check passes with flying colors.
Wow. So it has no idea that those two things shouldn't interact like that.
Right. The compiler has no idea what a book actually is in the real world, or that music is an intangible concept. It just knows you followed the structural rules.
Okay, so it just checks if the puzzle pieces fit, not what the actual picture is.
Precisely. It isn't until dynamic semantics comes into play, which is the runtime behavior, the moment the program actually executes in the real world, that the disaster happens.
Right, because it tries to do the impossible.
Exactly. Your syntax was perfect, the compiler gave you a totally green light, but dynamically, when the code actually tries to physically lift the book and slide the music underneath, the whole system crashes.
It realizes way too late that the action is just fundamentally impossible.
Yep. So if you're listening to this and wondering why your favorite app suddenly crashes out of absolutely nowhere, that's exactly it.
The developers wrote something that passed the static spelling check, but completely failed the dynamic reality check.
You got it. And actually, that leads to the final linguistic layer Dr. Okwu mentions, which is pragmatics.
Pragmatic, so that's about, like, real-world usage.
Yeah, you can write code that works, sure, but is it readable? Pragmatics is about writing software that the next human engineer can actually understand and maintain.
Which is huge, right? Because code is read by humans far more often than it is written.
Exactly. You write it once, but a dozen people might have to read it and fix it over the next 5 years.
Okay, so we have this linguistic structure. We have the grammar, the meaning, the readability. But language has to describe a physical reality. When we speak this code, we are fundamentally talking about data.
Yes. And that data isn't abstract. It needs a physical place to live inside the computer's memory.
It requires literal matter and space. I think that's something people forget. When you declare a variable, you are commanding the operating system to carve out a microscopic piece of physical silicon in your RAM to hold an electrical charge.
That's a great way to visualize it. It's real estate.
So since anyone listening to this deep dive likely already knows the primitive data types, like we all know integers, booleans, floating point numbers, let's skip the basic definitions.
Good call.
What's far more interesting to me is how the hardware actually treats those basic primitives versus the massive, complex, non-primitive data types that programmers build, like custom objects or, giant arrays.
Right, because whether it's a simple true or false Boolean or a giant heavy user database, it has to go into one of two main memory domains.
The stack or the heap.
Exactly. And the physical mechanics of how these two domains operate dictate the performance of literally every piece of software on Earth.
So let's break them down. Let's start with the stack.
So the stack is incredibly rigid, it's highly organized, and it's temporary. It operates on a strict last in first out basis.
Which makes me think of like a literal stack of heavy dinner plates.
Yes. Perfect analogy. You can't pull a plate from the middle. You can only take the top one off.
Right. But why does that make it so fast? The node kept mentioning how fast it is.
Because the stack uses contiguous blocks of memory. The CPU has a dedicated register called the stack pointer. When a function runs, it just slaps its local variables onto the top of the stack. And because it's all perfectly sequential, the hardware doesn't have to search for anything. It just moves that pointer up and down.
So when the function finishes,
the pointer just drops back down, instantly forgetting the data above it. It's automatic hardware level speed.
that makes total sense for small, predictable things where you know exactly how much space you need. But then there is the heap.
Ah, yes, the heap.
And honestly, the name heap makes it sound like my chaotic pile of laundry on the bedroom chair.
I mean, you're not wrong.
So why would anyone use a messy heap of memory when the stack is so blazingly fast and organized?
Because you simply don't have a choice. The stack's speed comes from its rigidity, right? It requires the exact size of the data to be known at compile time.
Oh, I see.
But what if you're building a dynamically growing list of user profiles? Or, say, you're loading a massive 3D texture in a video game?
You have no idea how big that data will get while the program is actually running.
Exactly. If you tried to put that on the stack, it would instantly overflow it and crash the machine.
If you throw it in the laundry pile.
You allocate it on the heap. The heap is this massive, flexible pool of memory. But there is a heavy, heavy performance cost.
Because it's not sequential.
Right. When you ask for space on the heap, the operating system has to actually pause, scan the memory for an empty block big enough to fit your massive object, and then return the memory address, the pointer, back to you.
Which takes time. And here's where it gets incredibly dangerous, right? Because unlike the stack, which cleans up after itself automatically, the heap requires manual housekeeping.
It is the single biggest source of headaches in software engineering.
I can imagine.
When you use the heap, the programmer has to explicitly tell the computer, hey, I need space, using commands like new or malloc. But crucially, they also must remember to manually free that memory when they are done.
Okay, let's ground this for a second. I mean, if you're a gamer, you've definitely experienced this.
Oh, for sure.
You boot up a game, and it's running beautifully at, 60 frames per second. But then 2 hours later, your computer fan is screaming, and the game is totally stuttering at like 5 frames per second.
It's the worst.
And why does that happen? Because somewhere in the code, a developer spawned an enemy character dynamically on the heap. But when that enemy was defeated, they forgot to write the delete command to free the memory.
Yes, a classic memory leak.
So the computer just thinks the enemy's still there, taking up space.
Exactly. Every time an enemy spawns, a new chunk of the heap is permanently locked up. Do that 10,000 times over 2 hours, and suddenly your computer has zero memory left.
The OS just starts panicking.
It desperately tries to shuffle data around the fragmented heap, and your performance absolutely tanks.
Which perfectly explains why we need structured ways to organize all this data before it hits the memory.
Yes, data structures are critical.
The material outlines data structures, dividing them into linear like arrays and queues where data sits sequentially, and nonlinear like trees and hash tables.
Right.
I'm assuming you use a nonlinear structure when you have like way too much data to just read it straight down like a simple list.
Exactly. Think about it. If you have an array with 10 million user records and you want to find one specific person, you might have to check all 10 million slots one by one.
That's a linear search.
Right, and it takes forever. But if you organize that exact same data into a nonlinear tree structure where every split halves the possibilities, you can find that exact user in about 20 steps.
That's a massive difference.
It is. The structure you choose fundamentally alters the physical time it takes the CPU to find the data.
Okay, so our data is parked in the heap, elegantly organized in a tree structure, and our primitives are zipping on and off the stack. But memory is just storage. Without action, it's just a warehouse full of boxes.
Right. We need to direct the movement of this data.
So if the data types are the nouns of our language, we need verbs. We need a steering wheel.
We need control structure.
There are 4 fundamental ways to direct traffic here, according to the notes. First is sequential control, the default. Top to bottom execution, line 1, line 2, line 3.
Boring, but the backbone of everything.
Yeah. Then you add selection control. Decision-making, the if and else statements. This is where the code actually becomes dynamic. Like, if the user is an admin, show this screen, else show the standard login screen.
And then there's iteration, looping.
The for loops.
Lists. The ability to tell a computer to do an incredibly piteous task 1 billion times in a fraction of a second until a specific condition is met.
And finally, jump control, where you force the execution to instantly teleport to another part of the program entirely. And this brings us to the infamous goto command.
Oh boy, the goto command.
Yeah, the notes explicitly warn that overusing goto leads to unstructured, messy spaghetti code.
No, but you think about it intuitively, jumping around seems incredibly powerful. If you want the code to do something over there, why not just go to that line?
Well, it goes back to what we just talked about, the stack.
Oh, really?
Yes, the entire architecture of modern software relies on predictable function calls. When function A calls function B, it pauses, leaves a sort of bookmark, and expects function B to return a value so it can continue. It's like a chain of custody.
Exactly. The go-to statement completely obliterates that chain of custody.
I mean, it doesn't leave a bookmark?
No. It violently rips the execution flow out of the current context and drops it randomly in the middle of somewhere else. The stack frames get completely desynchronized.
Oh, wow.
It's like reading a choose-your-own-adventure book, right? But someone has ripped out all the pages, shuffled them, and scattered them across the room.
That sounds like a nightmare.
It is. You jump from page 4 to page 82, then back to page 12. You completely lose the narrative thread. If the program crashes, you have zero idea how it got to that state.
That perfectly sets up the next major architectural concept Dr. Okwu brings up, data flow. Because it's not just about how the execution jumps around. It's about how the actual data moves between these different sections of code.
Right, and there's a massive debate here between explicit data flow and implicit data flow.
Okay, break that down for us.
Well, explicit flow is the gold standard of engineering. The movement of data is visibly documented right there in the code. You pass a variable explicitly into a function as a parameter, and the function explicitly returns a modified value.
So you could literally physically trace the pipeline of data with your eyes. But if
Exactly.
you're listening, you might be thinking, well, explicitly passing data around all the time sounds exhausting. Why not just put the data in a central location where every part of the program can access it whenever it wants?
Which is implicit data flow, using global variables.
Yeah, it feels like a cool shortcut.
It feels like a shortcut until something breaks. Think of your program's memory like a financial system. Explicit data flow is handing someone a physical written check.
There's a paper trail.
Right. You know who wrote it, who received it, and exactly what the amount was. An auditor can trace it perfectly.
Let me guess. A global variable is like having a massive shared bank account for the entire town.
It's exactly like that. Implicit data flow via global variables means any function, anywhere in the program, can walk up to that shared bank account, withdraw money, or deposit money without notifying anyone else.
Oh my God, I can see the debugging nightmare already. You run the program, the account balance is suddenly completely wrong, and you have to figure out who did it.
But there are no logs. There's no paper trail.
You literally have to audit every single person in the town.
Yep. In a large software project with millions of lines of code, if a global variable holds the wrong value, you are forced to search the entire codebase to find which obscure, unrelated function secretly modified it in the shadows.
It makes the state of your application fundamentally unpredictable.
Exactly, which is why modern programming languages heavily restrict implicit flow.
Okay, so let's zoom out for a second. We have a perfectly structured program. We mapped out the grammar. We've got our data cleanly routing through the stack and the heap. We're avoiding spaghetti code and explicitly passing variables to maintain a clean paper trail.
Sounds like a beautiful piece of software.
Right. But there is a massive elephant in the room that we haven't addressed at all.
The physical hardware.
Yes, because everything we've talked about, the syntax, the if statements, the arrays, that is still human text.
Right.
It's high-level abstraction.
Right. It's for us, not the machine.
The physical CPU underneath the keyboard doesn't speak Python. It doesn't know what an if statement is. It only understands voltage. High voltage, low voltage, 1 and 0.
Exactly.
So how do we cross that massive canyon from a human-readable while looped down to physical silicon execution?
This is the journey of translation, and it happens through layers of abstraction. At the very top, you have high-level languages, things like Python, Java, Ruby.
Where they use actual English words like class, print, and return.
Right. They're designed specifically for human brains to compose logic easily.
But to get closer to the metal, you have to step down a tier, right, to middle-level languages like C.
Yes, you strip away a lot of the safety nets. You start dealing directly with memory addresses using pointers. You're getting your hands dirty.
And then you drop even further into low-level assembly language.
Where the English syntax is just completely gone, you are now writing mnemonic codes, MOV, ADD, JMP.
So you aren't dealing with variables anymore. You are commanding the physical hardware registers inside the CPU chip to move bytes around.
Exactly. And the final drop from there is machine language. Pure binary, the raw voltage instructions.
But to get from the high-level English text all the way down to that machine language requires a brutal translation process.
It does. And this brings us to one of the most critical architectural decisions in computer science: compilation versus interpretation.
The method you choose dictates how your software will behave in the wild.
Totally.
Now, obviously, pre-translating everything is the best way to go, right? Compilation is like taking a novel written in Spanish, giving it to a translator, and printing 1 million copies of a finished English book.
That's a good way to look at it.
You do the hard work of translation once, upfront, into an executable file, like a .exe. And because it's fully translated beforehand, when the user double-clicks it, it runs with blazing speed.
It's very fast, yes.
So why would we ever do anything else?
Well, let me ask you this. What happens when you hand that beautifully printed English book to a user who only reads French?
Oh, it's totally useless.
Exactly. The main problem with compilation is hardware dependence. When you compile a program into binary, you are compiling it for a very specific CPU architecture and operating system.
Oh, so a Windows executable is fundamentally incomprehensible to an Apple M series chip.
Yes. If you want your app to run on Mac, Linux, and Windows, you have to manage 3 completely separate compilation pipelines.
Which sounds like a massive headache.
Yeah.
And that introduces the alternative interpretation.
Right.
So if compilation is a printed book, Interpretation is like having a live UN translator standing next to you, whispering the translation into your ear, line by line, as the code runs.
That's exactly it. The interpreter translates and executes the code on the fly. And the massive benefit here is incredible portability.
This is how JavaScript works on the web, isn't it?
Yep. You write the code once, and as long as the user has a web browser with an interpreter built in, it will run on any device in the world instantly.
But the catch has to be speed. Because you are translating and executing simultaneously, there is a massive performance bottleneck. You're constantly waiting for the translator to finish the sentence before you can act on it.
Exactly. It's inherently slower, which is why the industry didn't just settle for those two options. They created a hybrid to solve the problem.
JIT, just-in-time compilation.
Yes, JIT.
This is what the Java virtual machine uses, right?
Yeah.
How does JIT actually bridge that gap between the two?
It is honestly a brilliant compromise. When you launch a JIT-based program, it starts out acting like an interpreter. It's reading an intermediate bytecode, translating it line by line. But while it's doing this, the JIT compiler is quietly profiling the software in the background. It is watching the execution flow and looking for hotspots.
Hotspots, like areas of the code that are getting hammered repeatedly.
Exactly. Say you have a for loop that processes 1,000,000 pixels on the screen. An interpreter would stubbornly translate that exact same block of code 1,000,000 separate times, which takes forever.
Right.
But the JIT compiler spots that heavy traffic, it pauses, steps in, compiles just that specific loop directly into hyper-optimized machine kern, and caches it in memory.
Oh, wow. So the next time the program hits that loop, it completely bypasses the interpreter and just runs the raw compiled binary at lightning speed.
You got it.
To stick with the UN translator analogy, it's like the live translator realizes the speaker is going to read a highly repetitive legal document.
Right.
Instead of whispering the same phrases over and over, the translator frantically prints out an optimized translation of just that section, hands it to you, says, "Here, read this part directly." It's way faster.
It gives you the absolute best of both worlds. The cross-platform portability of an interpreter, because you're still distributing bytecode, combined with the blazing localized speed of a compiler right where you need it most.
It literally translates the code just in time for optimal execution.
Exactly.
That is incredibly elegant. So, stepping back and looking at this entire journey today, we started at the absolute ground floor with the basic phones and grammar rules of code.
And we saw how compilers rigorously check that syntax before allowing execution.
Right. Then we mapped out how the data we create takes up physical space, dynamically shifting around the heap or stacking up neatly.
We steered that data explicitly to avoid the debugging nightmares of implicit flow and spaghetti logic.
And finally, we watched compilers and interpreters bridge that massive divide between human intent and machine voltage.
It really emphasizes that the digital world we live in isn't built on arbitrary magic. It's built on meticulously structured language and incredibly strict physical rules.
Which leaves me with a final thought for everyone listening. Throughout this deep dive, the one recurring theme is that computers demand absolute explicit instruction. They despise implicit data flow.
They do. They crash if a single semicolon is out of place.
Right. They need every boundary checked and every command clearly stated with zero ambiguity. But human communication is the exact opposite.
Oh, we rely almost entirely on implicit flow.
Exactly. We read the room, we understand context, we pick up on sarcasm, body language, and unspoken cues. We almost never say exactly what we mean with perfect, machine-like, explicit syntax.
Thank goodness, or conversations would be exhausting.
Right. But as artificial intelligence models grow more advanced, and as we integrate these algorithmic systems deeper into our daily lives, something has to give. Or are we going to have to architect a way to teach machines how to process the messy, implicit, context-heavy way that humans actually communicate?
That's the million-dollar question.
Or, to avoid the inevitable crashes, are we going to find ourselves adapting to the machines? Learning to speak to each other with the rigid, explicit certainty of a compiler? Something to mull over until next time.